Okay, welcome to week 6, part 1. We're going to introduce the idea of Avl trees, which were the first kind of self-balancing binary search tree that was discovered. And we'll talk about the benefits that Avl trees have, and we'll get a start anyway at looking at how to code these things up. Okay, so in a binary search tree, as we know, every node in the tree has a value as well as a left child and a right child. Our convention has been that, and this is the convention that pretty much everyone uses, is that all values to the left of a given node are less than that current node's value, and all values to the right of the current node are greater than that current node's value. Now, because it's possible to enter values into the tree in a substantially ascending order or a substantially descending order, or because your modifications to the tree, such as deletions from the tree, might cause your tree to become more linear, the worst case search time, and therefore the worst case insert time and delete time, is order n. And we would like to avoid having that ever happen. We talked about the idea of a balanced binary search tree. If at every node the height of the left subtree and the height of the right subtree beneath that node is within 1, then the tree is said to be balanced. And a balanced tree guarantees order log n search performance, and therefore also insert and delete performance as well. Previously, we took a look at using Day's algorithm to balance an unbalanced binary search tree, and this is a pretty efficient algorithm, but it's certainly not the kind of thing that you would want to run on a frequent basis. If you have a binary search tree that's badly unbalanced, then you're probably well off to run Day's algorithm to get it back into balance. But ideally, we would have a binary search tree that maintains itself in balance rather than having to run, rather than having to come up with some kind of heuristic for how frequently to run Day's algorithm to get it back into balance. Okay, so the idea of a self-balancing binary search tree is a binary search tree that remains balanced, or at least approximately balanced, every time we do an insert or delete. We looked already at red-black trees. These are nearly balanced trees. The black height of the nodes in a red-black tree are maintained in a balanced way. So these do have, at the limit, order log n performance. The very first kind of self-balanced binary search tree that was discovered is called the Avl tree. And I suppose it would be nice if Avl stood for something that helped you remember what the tree is about, but actually it's the initials of the 2 Soviet mathematicians who discovered and wrote about this algorithm. So okay, well, I'm not I studied Russian once upon a time, but it was back in the previous century, and I'm not going to trust my pronunciation skills here. So Adelsonvelsky is where the AV comes from, and Landis is where the L comes from. It's significantly less complicated than a red-black tree, but still rather complicated to code. In concept, it's fairly straightforward, so let's get into it. So an AVL tree is an example of what's called an augmented data structure. That is, you keep track of the same information that you do in a binary search tree. Every node in the binary search tree has a value and a left child and a right child. But we also keep track in each node in an AVL tree of the balance factor, which is the difference of the height of the left-hand subtree and the right-hand subtree. Okay, so we're going to define the balance factor at a particular node to be the height of the left subtree minus the height of the right subtree. There appear to be differences of opinion about how to define the balance factor, and many people define it this way, other people define it the opposite way. It doesn't really matter as long as you're consistent. So if the height of the left-hand tree is greater than the height of the right-hand tree, so that the balance factor is negative, all right, well, I said that backwards. If the left-hand tree has a greater height than the right-hand tree, so that the balance factor is positive, then we say that that's a left-heavy tree. Okay? On the other hand, if the balance factor is negative, it's a right-heavy tree. And if the balance factors are the same, then we might say that they're balanced, but only at that particular node. Okay? We compute a balance factor for each particular node, using this formula. Now, in an AVL tree, so here is an AVL tree of integer values. It's the same as the original binary search tree diagram that we looked at a while ago. But in this case, we have augmented each node to include the balance factor. Those are the numbers in red here. So starting at the top of the tree, the topmost node here is 12. It has a value of 12, I should say. And the height of the left subtree is 2. The height of the right subtree is 2. Therefore, the balance factor at that node is 0. And actually, for most of the nodes in this tree, the balance factor is 0. The one exception in this example is the node containing 13. The left subtree has a height of 0, and the right subtree has a height of 1. So 0 minus 1 is where we get our minus 1 balance factor from for that particular node. All right, so if we're going to implement an AVL tree, then as we did with our binary tree, we're going to need to describe each node in this tree. This is going to be a nested class, a private class within the AVL tree class, and it will have a dunder init function. We pass in some value when we create an AVL node. We assume when we're creating a node that the left and right subtrees are empty, so we've got none as the default values there. Okay, and so for underscore value, we use the value passed in. Likewise, underscore left and underscore right. Sorry, I keep wanting to say data members, which is the C++ terminology. Instance variables. So the dunder value, the underscore value, underscore left, underscore right, private instance variables take on the values of these parameters, value left and right. And we're also going to add now, we're going to augment this data structure with a balance factor at each node. By definition, every time we create a node, that's going to be at the bottom of the tree, and so we'll just set the value 0 as the initial value for the balance factor of every newly created node. Each time we insert or delete a node, in an Avl tree, we have to maintain what's called the balance factor invariant property. That is, the balance factor of every node in the tree has to be, in absolute value, less than or equal to 1. So we say that our tree is an Avl tree if the balance factor in each node, after proper updating, whenever we do an insertion or a deletion, is a -1 or a 0 or a 1. Okay? So if the balance factor is -1, that means that the tree at that particular position, that node at that particular position, is slightly right heavy. If it's 1, it's slightly left heavy, and if it's 0, that means it's balanced at that particular node. And this really is essentially the same as the definition of a balanced tree. So if we are able to maintain this balance factor invariant at every single node in our Avl tree, then it's clear that the tree is balanced. Okay, now, whenever we insert a new node, the new node is going to be inserted at the bottom of our binary search tree. An Avl tree is a binary search tree. It's just a binary search tree that is balanced. So we only need to update these balance factors among the ancestor nodes of the new node that we have inserted. That is, the new node's parent, the parent's parent, the parent's parent's parent, and so forth up to the top of the tree. So that means that in an n-node tree, we need to check the balance factors of log n of those nodes when we insert a new node into our tree. Whenever we discover, as we check these balance factors, the balance factor at a particular node, as a consequence of our insertion, has either diminished to -2 or increased to +2, we're going to resolve that problem immediately by doing an appropriate rotation to restore the invariant, that is, to reduce these magnitude 2 balance factors down to 1 or 0. And there are 4 different cases of rotation that we might need to consider, illustrated here on the next couple of slides. So if the new node that, the new node that we're inserting here is the node at the bottom. In terms of the relative ordering of these nodes, the blue node is the node with the lowest value, the green node is the node with the highest value, and the yellow node has an intermediate value. So we could end up with a tree that looks like this, where the top node has a left child, and that left child in turn has a left child. The balance factor for the bottommost node that we've just inserted is, of course, 0 because it has no children. For its parent, the balance factor is +1 because there's the height on the left side is 1 and the height on the right side is 0. And for the grandparent, the balance factor is +2 because for the grandparent, the height on the left is 2 and the height on the right is 0. So we've discovered a situation where the balance factor invariant is not being held. And the solution to that is fairly straightforward. We do a right rotation on the grandparent node. And remember that that any rotation has the effect of pulling down the node that you're doing the rotation on. So in the case of a right rotation of the grandparent, you can imagine, grabbing that node as like a faucet and turning it to the right, and that will pull that node down below its left child. That will have the side effect of making the left child be the new parent of both the original leftmost node and the parent. And a nice side effect of doing that is that the balance factors, I describe it as a nice side effect, but it's a critically important thing that the balance factors for all three of these nodes now become 0. So at least this part of our binary search tree, of our AVL tree, is back satisfying the Avl Tree invariant. Okay, so that's one case. If our newly inserted node leads to a situation like this, then a single right rotation of the grandparent will solve the problem. And then we have the mirror case, no big surprise. In the mirror case, where the topmost node has the lowest value, and the newly added node is the one with the highest value, then we simply do a left rotation on the grandparent. And notice that gets us back to exactly the same relative ordering and exactly the same shape that we had in case 1. Okay? So all 4 of these cases are going to result in us taking an unbalanced 3-node tree and turning it into a perfectly balanced 3-node tree. The next 2 cases are, instead of being symmetrically to the left or symmetrically to the right, here we have a left-right situation or a right-left situation. Now, the balance factor for the topmost node here is a +2 because the height to the left is 2, whereas the height to the right is 0. Although notice that the height of the child of the parent, the balance factor of its child is -1 because it has a child on the right-hand side and no child on the left. Okay, so in magnitude, we've got 0 for the bottommost node. That is the balance factor. And then -1 for its parent and +2 for its parent. And this requires us to do 2 rotations. We do a left rotation on the parent. And notice that by doing a left rotation on the parent, that puts us back into the symmetric case that we dealt with as example 1. So having done a left rotation on the parent to move the parent below the newly added node, we then do our right rotation on the grandparent to get the perfectly balanced tree that we wish. The final case is the mirror case of that. Okay, this time we have the root node has a height of 2 to its right side and a height of 0 to the left. And it won't be a big shock to realize that we're going to do the mirror of what we did in step 3, or condition 3, situation 3 maybe. We're going to do a right rotation on the parent of the new node to move it below the parent, and then a left rotation on the grandparent, again to get back to our perfectly balanced node. Okay, so how do I know that these are, that this is it? Well, let me pull up a Python shell. Sorry for the gymnastics here. Okay, I'm going to pull up idle and get it to fit in my recording area. Too tall. Okay, so we've got three values. Let's suppose the values are, 1, 2, 3. And the question is, how many permutations are there for these three values? Well, that's going to be 3 factorial is 6 different possible permutations. I should have done this as a comment because I'm not really trying to write code here. In other words, we're going to have 1, 2, 3. We're going to have 1, 3, 2. We're going to have 2, 1, 3. Yeah, I'll save some space and just say 1, 2, 3. 2, 3. 1, 3, 2. 2, 1, 3. 2, 3, 1. And 3, 1, 2. And 3, 2, 1. And these result... Okay, so those are the only possible orderings in which we could have added nodes to our tree. And the 1, 2, 3 case results in this situation where all the nodes are on the right side, and we have to do a right rotation of the parent to get to our perfect balance. All right, so that's the 1, 2, 3 case. Then the 3, 2, 1 case is the opposite of that. It's the situation where all of the nodes go to the left. 3, 2, 1. Now, 1, 3, 2, pardon me, 2, 1, 3 and 2, 3, 1 are already perfectly balanced. 2, 1, 3 gives us a 2 at the root with a 1 to the left and a 3 to the right. And it doesn't matter whether we do the 1 before the 3 or the 3 before the 1. As long as we have the 2 at the top, we're good. So the other cases here are 1, 3, 2 and 3, 1, 2. Okay, where 1, 3, 2 is the right-left case, and 2, 1, sorry, 3, 1, 2 all right. Yeah, so 1, 3, 2. 1, 3, 2 is the right then left case, and 3, 1, 2 is the left then right case. All right, so those are the only possible 6 ways or 6 orders in which we could have put values into the binary search tree. And because 2 of them are balanced at the outset, we know that the other 4 are the only other possible combinations we need to worry about. And it turns out that we're going to recursively apply this rule upward through the tree as we adjust the balance factors on the node, moving upward from our newly added node upward to the ultimate parent. Each time we discover that our balance factor has become a -2 or 2, we'll immediately do a rotation of 3 nodes, and that will solve the problem. Okay. Now, one thing that will occur to you quickly is, since we're doing all these rotations, how does each node know where its parent and grandparent are? Should we implement our binary search tree in such a way that every node keeps track of its parent as well as its left child and its right child? It turns out we don't have to do that, because since inserting a new node or deleting a new node only damages the balance factors among the ancestors, we can simply put together a list of the parents and grandparents and great-grandparents as we descend through the tree, and that way we will know exactly what our parent is, what our grandparent is, what our great-grandparent is, and so forth, all the way back to the top of the tree. Okay, so here is part of the insert code. And this part of the insert code only handles values that are going to the left side of the tree. You may recall when we implemented the binary search tree before that we needed an if to handle situations where the new value that we're adding is less than the current node's value, and then we had an else down here to handle the situation where the node's value was greater than the current node's value. And because we're doing strictly a less than test and later on a greater than test, we avoid a situation of having duplicate values in our tree. So this is the same idea as that binary search tree code we looked at before, but we're calling this our Avl Tree class, and we're using the Avl node class. This is going to invoke the dunder init function for the Avl node class each time we add a node to the tree. So the first insert we do, the top is none, and so we just put our newly added node at the top. Now, if there's already a node in the tree, however, so that self.top is not none, we're going to drop down and call ourselves our recursive helper function. And notice what we've changed. Instead of just passing self.top as the current node, we're passing a list containing self.top as the list of all the ancestors of the node that we plan to insert. Okay, so if this is the very second node that we're inserting, then this list is only going to consist of self._top. All right, so we're passing the list of ancestors and the value that we want to insert. Okay, so the direct parent of the new node that we're going to insert is right at the beginning of that list of ancestors. Therefore, if the value we're trying to insert is less than the parent's value, we're going to check the left-hand side of the parent. Well, if the parent's left-hand side is none, then we simply add a new Avl node at that left-hand side. That may cause the balance factors to be messed up, and so we're going to call this update function to check all of the balance factors and to call rotate functions as necessary to bring the balance factors to match the invariant. Okay? Now, notice that when we call the update function, we don't really care about the value that we're trying to insert anymore. It's been inserted. It's fine. All we care about is the list of all the nodes from the current node all the way up to the oldest ancestor. And so the list of ancestors that we're going to pass down, including this current node that we have just added, is the concatenation of a list containing just the new node plus the list containing previous ancestors. So that will have the list of ancestors in the correct order. We've got our current node, we've got its parent node, then the parent's parent, the parent's parent's parent, and et cetera, et cetera. On the other hand, if the left subtree already has stuff in it, we're going to need to call insert help, once again adding the left-hand node as an ancestor of the new node that we're going to add, and passing down v here. Okay? All right, so this only handles traversing down to the left-hand side. You need to create the analogous code for traversing down to the right-hand side. Okay, so let's suppose that we insert 20 into an empty tree, okay? So we call insert for the first time. The value that we're passing in is 20. Self.top is none, so we're going to create an AVL node right away with the value 20 put in place, and the balance factor is going to be 0 because this is a newly allocated node, and the newly allocated node doesn't ever have any children, or at least not the way insert is using it. The newly allocated node does not have any children, and therefore the difference in height between the empty left and right children is going to be this balance factor of 0. Okay, and we store that into the top node, and that's it. We're done. Now, let's suppose that the next value we insert is 7. Okay, so 7 comes in as our value. Self.top is not none now, so we're going to call our insert helper with a list of all the ancestors of the new node that we'll eventually create. And at this point, the list only consists of top. So we've got a list just containing top, and we passed on the value. So pars means parents. Okay, so pars is my parents list, and pars sub 0 is top at this point. So we're testing whether the value coming in is less than top's value. I see I made a typo here. That should be underscore value. Oh, and these guys should be underscore left. Sorry about that. Yes, okay. So I apologize. I have forgotten my underscores in some of these slides. Okay, so since 7 is less than 20, we're going to check whether the left subtree of the ancestor, of the parent, that is of top, is none. And it is, so we will create a new node containing 7, and the left side of the parent will refer to that new node containing 7. And now, because I've added my node, I need to update the nodes from the newly added node up to its ancestors to make sure that they all have correct balance factors. And we can see, in this case here, this is illustrating what's going on before we call update. And notice that the balance factor up here in the parent is 0, but we've just added a new node to the left, so that balance factor needs to be updated to be a +1. Okay, because +1 indicates that at this node the tree is left heavy. Okay, and so here is a sketch of part of our update function. Okay, so to update, we receive this list of ancestors. Actually, the first item in the list is the current node that we have just added into our tree. And we're going to use a counter that we'll just call P, maybe that's a bad name, to step through the items in this list of parent nodes. Okay, now N is going to be the current node, P is going to be the parent of N, and G, which it turns out we don't need yet, is going to be the grandparent of N. We want to make sure that that our value of P remains within bounds, and what we mean by that is we want to make sure that our value of P, our subscript P, will stop being increased when we get to the point where there are no more parents left. Okay, so ln of pars is the length of all the ancestors. That minus 1 is the maximum subscript that we can use that still has a parent remaining. Okay, so N is pars sub P. P is pars sub P plus 1. And we ask, all right, is this newly created node a left-hand child of its parent? Well, in this case, it is. The newly allocated node is the left-hand child of the parent. And is the balance factor of the parent greater than 0? Okay, if the balance factor of the parent is greater than 0, then that means that when we add one more, this balance factor will become greater than 2. Well, it will become greater than or equal to 2. Okay, if it's greater than 0, the only thing it could be is plus 1. So when we add another node to the left, that will increase to plus 2. And consequently, if this child node is a right-heavy node, that means that we have a left-right situation, and so we're going to have to do a left-right rotation. But actually, because the parent's balance factor is less than 0, that means that we don't have a third node down underneath here. We've only got 2 levels. And so we're actually going to skip over this rotation stuff, and we're just going to increase the parent node's balance factor by 1. So following the update, here's what we've got. So this pars that comes into our update function consists of the newly added node the newly allocated node is in a list concatenated with the list of all of the ancestor nodes. So our list of parents is just the current node and its parent. Because PBF was not greater than 0, here we come down and increment PBF, the parent's balance factor, to plus 1. And we're done. Okay, now, this is just the very simplest case. And obviously there's, there's the symmetrical case and so on. So there's there's a lot of code left out there on slide 16. Okay, now we're going to insert minus 4. And let's see what happens with our insert function. Whoops, come here. Okay, so now we're going to insert -4. We call insert with -4. Self.top is not none, so we're going to call self.insert help with top as the original parent list and -4. When we drop into insert help, -4 is less than 20. All right, par sub 0 is self.top. Self.top.value is 20, and -4 is less than 20. So we drop down and check. Is the left side underneath top none? Well, no, it's not. So we have to drop down to the else and do an insert help. Notice now that we're creating a list containing the left-hand side reference, the reference to the node containing the 7, plus the list containing all of the other ancestors. All right, so we're passing a reference to the 7 concatenated with a reference to top and -4. All right, so we come up here. This time through, pars has two values in it. It's referring to the 7 and to the 20. Is -4 less than 7? Yes, it is. Is pars sub 0, remember that's now the left-hand side, is this value 0? Okay, and indeed it is 0. So we're going to add our new node containing -4 to the left side, and we're going to call update again with this reference to the new node, as well as references to the 7 and references to the 20. So here's what that update looks like. Okay, so we're going to call update again. And this time what's been passed in is a reference to the newly allocated node, followed by its parent, followed by its grandparent. And as we go through here, okay, N is the newly allocated node. P is the parent of the newly allocated node. If N is the left child of the parent, okay, that's true. And if P, BF, if the parents oh, no, I'm fine. Okay, this slide 19 shows what happens with the valence factors just prior to the rotation. Okay, so here we are here. We're asking, is the parent's balance factor greater than 0? And at this point, it's not. The parent's balance factor is 0. So we don't yet do a rotation. We increase the balance factor of this node to 1. Now, P has been incremented in here. We didn't get down to showing that. So now we're looking at I may have a typo in here. In any case, so our logic should discover that this balance factor has increased. It was +1, which is greater than 0. And that means we need to do some rotation. Now, if the newly added, if the bottommost of the threes nodes has a balance factor less than 0, meaning that it's right heavy, we're going to have to do a left and right rotation, a pair of left and right rotations. But that's not our case here, because n's balance factor is just 0. And consequently, we're just going to call a right rotation. And the right rotation is going to receive our subscript and the list of all the ancestors. In this case, the subscript is going to be 0, and the ancestors are going to consist of our node that we just added, plus its parent, plus the parent's parent. And now we need to deal with the grandparent. So we're going to make sure that the subscript that we've been given into our list allows for the existence of a grandparent. If the list of ancestors is so short that there is no grandparent, then there's no rotation to do. The right rotation requires doing a rotation around a grandparent. So we're only going to do a right rotation if a grandparent exists. We'll set n to be the first reference in our ancestor list. P is the next one, and G is the third one. Now here I have added what should be an unnecessary test just for debugging purposes, because we only want to do a right rotation in this circumstance, okay? This is our first rotation situation. And so we only want to do this right rotation of the grandparent if n is P's left, and also if P is G's left. So if n is not P's left or P is not G's left, we're going to bail out because we have been called incorrectly. But in this case, n is the left child of P, and P in turn is the left child of G, and so we're ready to do our rotation. And we need to test whether the grandparent is the top of the tree or not. It is the top of the tree, so we're going to execute the code where the grandparent is the top of the tree. And the rotation is pretty straightforward. We only have to change 3 references. We change the top to refer to P. We change G's left to refer to P's right. Okay, so what used to be the right-hand side of 7 now becomes the left-hand side of 20. And we need to change P's right to refer to 20. And when we've done those 3 reference changes, the balance factors, whoops, another typo here. There should be G.BF. The balance factors for all of these become 0 again. We have also now got this parent node is now at the top, and the old parent node no longer factors into our continued climb up through the ancestors. So you'll notice that I've thrown in a pop here to get rid of this middle ancestor. Okay, because we no we no longer have a reference to that node. We no longer have a copy of 20's old left-hand side, because now 7 has been elevated and 7 is now at the top. Okay? And so our list of ancestors has been reduced. Okay, so you can continue going through and trying more examples of adding more stuff. And in the live lecture, I plan to do quite a lot of that to try out various other scenarios. And as you can see, we've provided sort of a sketch of the beginnings of the code. I guess it won't shock you to learn that you're going to need to complete the code as the homework. And on Wednesday, we will get into taking a look at dealing with deletion, which is more painful than insertion. Okay, so I will see you then.